Hi everybody. This video concerns two quick facts about polynomials that are useful when you're trying to graph polynomials or when you're constructing the functions based on various information. So our first theorem is about multiplicity. So in the first bullet point we have, if the multiplicity of a factor or a zero is even, then the graph touches and rebounds from the x-axis at the x-intercept. So let me give you an example of what that means. So if we're talking about even multiplicity, you might have a polynomial function, and it could be a really high degree. So you could have a whole bunch of factors, but one of the factors has an even multiplicity, like 4. What this means is when you look at the graph of this polynomial at the x-intercept given by that factor, so if we were looking at the graph when x equals 3, then the graph would touch but not cross the x-axis at that point. So there are two possibilities. The function might be positive and touches the x-axis, and then it rebounds and stays positive. Or the other possibility is the graph could be negative, touches at the x-intercept, and then turns around and stays negative. You don't know which is which just by looking at this factor. You'd have to look at all of the other factors and see if they are giving you positive versus negative behavior when you're close to x equals 3. Now, the next bullet point says that if the multiplicity is odd, then the graph crosses the x-axis. And this is the behavior that you're more familiar with most likely when you think about x-intercepts. So if you have a function, a polynomial function, and it has a whole bunch of factors, but let's say one of the factors has an odd multiplicity, like 5, then you know that the graph has one of the following behaviors. Go to the x-intercept given by this factor, which is -2. Then the graph crosses the axis at that point. So it's possible that the graph is positive, you touch the x-intercept, and then you cross the axis. Or it's possible that the function is negative, you have your x-intercept, and then you cross over. So those are the possibilities for if you have odd multiplicity. Now, if you want a quick trick for remembering this, it's really simple. Just think about functions that you already know. For even multiplicity, think about the parent function parabola x squared. Well, that has even multiplicity at the x-intercept, which is the vertex of the parabola, and it points up. So when you think about even multiplicity, just think about y equals x squared, where you have a graph that touches but does not cross the x-axis. Then for odd multiplicity, think about the simplest, well, maybe you'd want to think about y equals x to the first power, but when you get into the reasoning behind this little theorem, you want to think about the third power function. But this is also a really simple parent function. You have an x-intercept at 0, 0. The graph goes up, the graph goes down, but the important part is that it crosses the x-axis. So when you're thinking about odd multiplicity, just think about this simple example, y equals x cubed, where the graph crosses the x-axis. So that's one of the theorems we wanted to talk about today, and there's one more. So I'm going to clear the screen and bring up the next theorem. So the next theorem has to do with conjugate pairs. Now there's some notation here that I didn't use in class, but we'll be able to digest it pretty easily. This theorem says if you have a polynomial with real coefficients, then if z is a 0, so in this context, the letter z lets you know you're talking about a complex number. So if a plus bi is a 0, so if you plug in a plus bi to your function and you get 0. Well, this theorem says that z bar, which is shorthand for the conjugate of z, so that is a minus bi, is also a 0. So that's all that says. Now the reason this theorem is true, I'll just sketch really quickly here. If a plus bi is 0, x minus a plus bi has to be a factor. I don't like this letter x. X minus a plus bi is a factor. Well, if this factor is in the middle of your polynomial, you're going to have some complex number coefficients. You're going to have an I. So to get rid of that, to balance that out, as we learned earlier in the year, you're going to have to multiply by the conjugate. So if you were to use the distributive property, this a plus bi times a minus bi, all of the i's will cancel out, and you won't have any complex number coefficients. Now, there's an alternative version of this theorem, which we also need to know, and it's for if you change the word real to rational. So if all of the coefficients of your polynomial are fractions or whole numbers, there's a version of this theorem that says if you have a number like 2 plus 3 times the square root of 5. Okay, if this number is a 0, then its conjugate, 2 minus 3 square root of 5, is also a 0. And it's for the same reason. If you form the factors, if you have rational coefficients, well, you can't have any square root of 5s in your coefficients. So to get those to balance out, you're going to have to end up multiplying by the conjugate. So long story short, in polynomials with real coefficients, complex number zeros show up in conjugate pairs. And then with rational coefficient polynomials, these sorts of radical or square root numbers show up in conjugate pairs. Anyway, these are two facts that are really useful when you're dealing with polynomials. See you next time.